from University of Carolina, and she's going to talk about illuminating the universe with dark matter and minihalos. Just a few words about her. She graduated from bachelor from Princeton in 2003, and then she moved to Cambridge for 1 year, and after that to Caltech for 5 years as a PhD student working with Professor Kamiokowski. Then she moved to Canada for a joint position between the Perimeter and CETA, and now she's a junior faculty at the University of Carolina. So, thank you.
Good morning. So I'm going to talk about how we can use something that we know virtually nothing about to learn about a period of the universe that we know even less about. How can we use dark matter to learn about the universe's first second? So a major question, this was working just a second ago, there we go, that is kind of the center of this talk is what happened before Big Bang nucleosynthesis? So this is the time when every cosmologist needs to take a little bit of a victory lap and say that Big Bang nucleosynthesis is one of the crowning achievements of cosmology. It successfully predicts the relic abundance of the light elements, and it tells us without a shadow of a doubt that the universe was radiation dominated at the time of BBN. However, we have good reasons to think that the universe was not radiation dominated all the way back to the Big Bang. The primordial density fluctuations that we see in the cosmic microwave background point towards an era of inflation. And inflation is most definitely not radiation dominated, it's dominated by a scalar field. Now, then it's thought that the inflaton somehow decays, but we still have other scalar fields as well that could come to dominate the universe after that. And there's a very famous example of this, the string moduli problem, in which the scalars with gravitational couplings that govern how the different dimensions in string theory fold and compact, those scalars very generically come to dominate the universe prior to Big Bang nucleosynthesis. So much so that this is a problem with a long history of it's actually rather challenging for these theories to get the universe radiation dominated in time for Big Bang nucleosynthesis. Maybe this is not being reliable enough to use. So let's start then with where we think the beginning was, inflation. How do we actually probe inflation? How do we know anything about inflation? So we mainly study inflation by studying the perturbations that were generated during inflation. So the idea is that we have some perturbation mode, quantum fluctuation, that gets stretched longer than the horizon scale, becomes frozen. At some later time, then another fluctuation is laid down on top of it, which itself gets stretched, while the first one is now even more stretched, and another fluctuation gets laid down on that. And this progresses during inflation. What we actually observe is the cosmic microwave background. It tells us something about what the inflaton was doing when these different perturbation modes left the horizon. And so the power spectrum that we measure is effectively a historical record of inflation, with the smaller wavelength perturbations corresponding to the later stages of inflation, like the yellow one here corresponds to time 3, as opposed to the long wavelength perturbation corresponds to time 1. So when you look at the primordial power spectrum of density fluctuations, you really are looking at like an archaeological record of what happened during inflation. And since we'd like to understand inflation more, if I stand over here, then it works. So here's the primordial power spectrum. So this is a power spectrum of curvature fluctuations as a function of wavelength. And this is our historical record of inflation. We know it extremely well over here at wavelengths of a few hundred megaparsecs. That comes from the CMB. And it's very flat and it's very featureless. However, this is only a small segment of the full historical record. The Lyman alpha force can get us to slightly smaller scales, but smaller than that, and we really are kind of in the weeds. We have a bound from primordial black holes, but it's incredibly weak. There's a nice bound from cosmic microwave background spectral distortions, that can kind of get us maybe halfway there. But a major bound that has been publicized recently comes from these ultra-compact minihalos, and that will be one of the first segments of my talk. Now,
of course, there is a filter at the short end, right? Due to the dark matter having some smoothing length.
yes,
The Jeans length.
yes. So some free streaming length that would prevent dark matter halos from forming over here. Absolutely. So, of course, what we generally do is we just extrapolate what we see on the CMB and extend it all the way down to arbitrarily small scales. But there could be surprises lurking, out here in the wilderness. Inflaton interactions can give you a spike in the primordial power spectrum. Multi-stage or multi-field inflations can give you kind of a step or plateau feature. We can have a runaway power spectrum. And then these waterfall inflation models end up with kind of a broken power law spectrum. So there are many inflationary models that predict interesting stuff going on these scales. So, kind of reorient you about where we are in the history of the universe. We have, here we are now at the cusp of dark energy domination. And we're going back to radiation domination. Here's our pin at Big Bang nucleosynthesis. In order to set the stage appropriately for Big Bang nucleosynthesis, the universe has to be radiation dominated at temperature of 3 MeV, which corresponds to about 0.08 seconds after the end of inflation. Then we have a gap. And then we have inflation, of which we really only have a good probe of the region about 60 E-folds before the end, and we're fairly ignorant of what happens after that. So this talk will kind of have two major ideas. How can we use minihalos to probe inflation? These are these so-called ultra-compact minihalos. And then part two, we'll be talking about probing this gap, the pre-BBN thermal history with microhalos. I'll generally use kind of the lexicon that helps that when I talk about a minihalo, I'm talking about usually something that's kind of solar mass to hundreds of solar mass. And when I talk about a microhalo, I'm usually talking about Earth mass or smaller. So there's my kind of jargon delineation. So part one, probing inflation with minihalos. So we're looking at the later stages of inflation. This is based on work that two recent publications that are led by my graduate student, Sten Delos. Let me make a aside here. Sten's been operating like a postdoc since the minute he walked into my office, and he'll be on the job market next fall. You should really, really, really make him an ITC fellow. This guy's amazing. He's phenomenal. I cannot sing his praises enough. So he did all this work. I'm just the messenger. So what is an ultra-compact minihalo? These were first proposed by Riccati and Gould in 2009. Think of them as failed primordial black holes. So what we're talking about is a region that enters the horizon with a density contrast greater than 0.1%, so 10 to the minus 3. In contrast, a primordial black hole requires a density contrast of more like 0.2, 0.3, so much higher. Those regions, these regions with density contrast higher than 0.001, will collapse at early times, like redshifts of 1,000, into ultra-compact minihalos. Can we then go out and look for these? So the formation threshold, if this is the probability of having a specific overdensity, this, as a function of overdensity, we think the fluctuations are Gaussian. And so there's some Gaussian distribution, and in order to make an ultra-compact minihalo, you need to have a density fluctuation up here in the high tail. So if we go out and constrain the abundance of ultra-compact minihalos, we can constrain the width of this distribution, which is, if you assume a locally scale invariant power spectrum, directly related to the primordial power spectrum of curvature perturbations. So this is how we're going to use minihalos to constrain inflation, is we're going to put limits on the abundance of these minihalos and then translate that into a bound on how the initial amplitude of fluctuations. And that's where this bound in red comes from. So you can see this bounded red is the fact that the Fermi gamma ray satellite has not seen dark matter annihilation within ultracompact mini-halos. And you can see it's actually a very powerful bond. It wipes out a lot of the unknown space, going down to pretty small scales.
But that presupposes that you've got dark matter annihilation.
So this presupposes that you have dark matter as a thermal relic, yes.
Yeah, so.
No, it's true. No, you were assuming that you have dark matter as a thermal relic. I actually, several years back, looked at whether or not you could hope to see these with microlenses, astrometric microlenses with Gaia. And yes, hold that thought.
Okay.
So these things were assumed to have this extremely steep density profile given by radial infall. And that's because they were thought to form in isolation, very spherical, no other perturbations around, and so they were thought to have the density profile given by just pure radial infall. If they have that density profile, then we also showed that you could do a pretty nice search with Gaia that would put down constraints about right here. And that would not be dependent on dark matter annihilation. And also it was part of the Thea proposal to do this with Thea. Yes?
I'm sorry, just to develop an intuition. So you're talking about z equals 1,000 and a fluctuation of 0.1%. So how high a peak height is that? Or like how rare are these peaks?
So this kind of gives you an idea. The constraint that there is not more than like 10 to the minus 6%, or a fraction of 10 to the minus 6 of the dark matter in these objects. So that constraining that they're about as rare as 6 sigma fluctuations is what wipes out this red region.
Oh,
So that puts the power spectrum upper bound at about 10 to the minus 7. So what we wanted to do though, so all these bounds and all the work prior to last year on ultracompact mini-halos, and there's been lots of it, assume this radial density profile. And we wanted to test that. Does this actually, is it really this density profile? And so what we did was we modified Gadget to include a smooth radiation component. That was actually the work of a summer intern, Avery Bailey, who worked under me a couple summers ago. He's now a graduate student at Princeton. And so we have now a modified Gadget that this shows the power spectrum at a redshift of 1,000 compared to at a redshift of about 10 to the 5, and the growth you get in our simulation in the linear regime compared to the linear theory prediction with radiation. So we've successfully incorporated radiation domination into Gadget and our initial conditions. Then we put a spike right here, a spike that would just be constrained by the standard bounds in our power spectrum and generated initial conditions. Even with a spike this high, an ultracompact mini-halo corresponds to about a 6 sigma fluctuation. So when given the size of our box, that means about a 1 in a million chance that there's one in our box. We actually generated lots and lots of initial conditions and searched for an initial condition that had, as a region that fulfilled the requirement to make an ultracompact mini-halo. So the regions that we have are not typical regions. They was purposefully selected to give the right environment to form one of these things. And then we made one. We ran the simulation. Here is one of our objects. So here it is a redshift of 1255, and it collapses as predicted right around a redshift of 1,000.
What's the mass?
So this thing collapses as a mass of about 3 solar masses. So this is a small box. So it's 3 solar masses, and the box size is 5 kiloparsecs over H. And this is a little zoom in.
Because I thought your spike was at 10 to the minus 3 megaparsec.
No. It was much further down from that.
According to the previous slide, it was. Anyway.
I can show you the spike we used. But yeah, it starts at about at a few solar masses and then grows. This is the initial density field in the box, and you can see that indeed there is this this box was selected for this region right here. And indeed, at a redshift of 715, this is the only halo in the box. So this is a freakish early forming halo that forms completely in isolation, just like the ultracompact mini halos were supposed to do. Now, by a redshift 100, we've got lots and lots of halos, which is not surprising because this is an enhanced power spectrum. So we've got lots and lots and lots of halos at a redshift of 100, and here's a zoom in of what our primary ultra-compact mini-halo looks like at a redshift of 100. So what does this thing's density profile look like? So this is the density profile scaled by r to the 3 halves to make it flat. The different colors show different redshifts, so ranging from redshift 400 to redshift 50. The inset actually just shows density as a function of radius. And so it's a broken power law. You can see that as it grows, the inner density profile is incredibly stable with redshift. And then it basically just continues to accrete mass in its outer regions. The inner profile asymptotes, this is very, very, very flat here, asymptotes to basically a Moore profile. And so we simulated 9 ultra-compact mini-halos, and they all have Moore profiles. And they all have Moore profiles that are extremely stable with redshift, with one exception. One of our halos experienced a merger at a redshift of about 86. So here it is at 134, and then another halo came in and pounded it, and the density profile before the merger was looking very Moore-like, and the merger did evacuate some mass from the inner region. So we don't have the resolution necessary to say definitively what the new profile is, but it does seem that mergers can disrupt the Moore profile. And this has been seen in other studies of standard structural information as well, that as you hit profiles with cusps in more and more mergers, they kind of tend towards NFW.
So the special feature of this power law index is that rho squared times r cubed is constant, which means that you don't get divergence in the annihilation. You understand that?
Yeah, then that's a major distinction between NFW and Moore. We'll come to that when we talk about the annihilation profile. So we also simulated a plateau. So yeah, maybe I should check the actual paper. Maybe I put this at the wrong scale. Maybe it's further in here. The actual paper has the figure of where the spike was. And so this is with a plateau in the power spectrum. And we have that this looks more familiar as a cosmological simulation because it is scale invariant over the box. So we have our initial density. Indeed, we form a halo very early. And this halo now looks much more typical of what we get with normal structure formation, which is not at all surprising. It is normal structure formation. It's just happening earlier with the scale invariant power spectrum. And so totally not surprisingly, these things, when we put in a plateau feature in the primordial power spectrum, we get an NFW profile. So this is again rho times r to the 3 halves. So a Moore profile, like I showed before, should be flat here. These ultra-compact mini-halos have a NFW fit, which again, in hindsight, should not be surprising. This is standard structure formation. It's just happening at a slightly earlier time. If you get NFW profiles in cosmological simulations, you should get NFW profiles here too. So this already is saying that what we have is a more complicated scenario. Ultra-compact mini-halos that form from spikes in the primordial power spectrum have Moore profiles, whereas plateaus give you NFW profiles. So going forward, what constraints you can put on inflation from mini-halos depends on what type of signal you're generating. It's not just a blanket, bound on the primordial power spectrum. It does depend on whether it's a spike or a plateau. And we're currently investigating kind of like where is the crossover line? How fat can the spike get before you turn into an NFW profile? This change to the dark matter, the profile reduces the signal, the annihilation signal, from an ultra-compact mini-halo by a factor of about 200, which in turn reduces the upper bound on their abundance by a factor of about 3,000. So this initially is bad news for using ultra-compact mini-halos to constrain the primordial power spectrum. However, this shows the simulation box for the spiked power spectrum at a redshift of 100, and our ultra-compact mini-halo is right in here, you can see that by a redshift of 100, we have lots and lots and lots of additional halos. These halos have been hitherto ignored. These previous bounds just only considered the ultra-compact mini-halos that form at a redshift of 1,000. They completely ignored all of these. So what happens if you include those? So this shows a representative sampling of the mini-halos in our simulation at a redshift of 100. The curves go in deeper because the light ones are smaller, so we have less resolution inside their scale radius. And indeed, you see there's a spread in their density profiles. They're all basically consistent with a Moore profile, but of course the amplitude's different. However, if you scale their density profiles, saying that their scale radius should be about the physical size of the spike at their formation, and that their density is proportional to the background density at their formation, then with those scalings, they collapse to a more universal profile, albeit with some scatter. And we're currently working on refining this model to try to cut down on that scatter. But this at least gives us a first pass for how to predict how formation time of halos maps to density profiles. Then we use the BBKS formalism of statistics of peaks, so the Berdeen, Bond, Kaiser, and what's the S? Thank you. Statistics of peaks to get the number density of halos as a function of formation time. So why do we use this instead of Preschecter? Preschecter, because it counts, clouds within clouds, it basically counts these things as destroyed if they fall into a larger halo later. But they're not really destroyed. They actually exist as subhalos. And so what we really want to count is just the number of peaks as a function of amplitude that would form at a given time. Now this does ignore mergers. So it's choose your poison. Preschecter always assumes that a merger destroys something, and that's not generally a good picture. This assumes that mergers never happen, which is not a bad picture for spiked power spectra. For spiked power spectra, because there's kind of a characteristic spacing between the halos, mergers are relatively rare. But this is just kind of a first pass. And from this, we can get new constraints on the primordial power spectrum. So as a proof of concept, we just applied this to a delta function spike. This is partly because of that merging issue. So we're just imagining a delta function spike in the primordial power spectrum and constraining its amplitude, or the integrated area underneath this spike. For comparison, we also use the standard ultra-compact Minihalos abundance constraints to obtain a corresponding bound on this power spectrum. And that's shown by the dashed lines here. So the red dashed line is from the diffuse flux of gamma rays, and the black dashed line is from gamma ray point sources. And our bounds are in the solid. So we actually do better than the old bounds, even though each mini halo has a weaker signal because of the shallower density profile. The fact that we're considering all the halos more than compensates for that, and actually leads to a stronger bound. The reason why our bound is so much more sharply peaked for where K is corresponds to the fact that our bounds are much more sensitive to changes in the Minihalos abundance limits. This is because instead of constraining 6 sigma fluctuations, we're basically constraining now more 2 to 3 sigma fluctuations. So we're a lot more sensitive. A little change in the abundance has a much bigger impact on the width of the distribution. And that's why this bites down so much. So we are refining this. This is still work in progress. But where are we now? The takeaway message is that the old bounds from ultra-compact mini-halos need to be thrown out. They have the wrong density profile. However, hope is not lost, because now that we have thrown away that density profile, there's no reason not to just open up our constraints to all the other halos that form from these enhanced power spectrum. And when we do that, we actually get stronger bounds on the primordial power spectrum. So, what are we working on now? Improvements are underway. We need to include the effects of mini-halo mergers. So as a first pass, we looked at what happened to our bound compared to the no mergers that I just showed you, to what happens if you change everything to NFW, assuming that everything experienced a merger is now NFW. And then also what happens if you then say half of the halos were destroyed from mergers. So that kind of gives you an idea of what mergers could do to these bounds. We're improving our model for the minihalo density profiles to try to bring down that scatter. We're looking beyond a delta function spike. And eventually the goal is to use this to constrain inflationary models. So that's kind of the end of point of part 1 and talking about inflation. So yes, this gives the actual, the scale of where the constraints are. Yes?
Which fraction of the dark matter ends up in those, roughly, in your...
So corresponding to these bounds?
Yeah.
So they basically, good question. So these bounds correspond to abundance. So the old abundance fractions on the old abundance, so about, at a redshift of 100, about 80% of the dark matter is in these halos.
Okay, because I mean, there are limits from gamma ray burst, for example, on probability of lensing and femtolensing.
Right, so
have you looked into that?
So not with the new density profiles. So as I mentioned, back in 2012, I looked at ultra-compact mini-halos in astrometric microlensing with the old density profile. Haven't looked at lensing yet with the new density profiles. That's on our to-do list. Now, my previous experience with lensing by dark matter halos, when I first started looking at astrometric microlensing by dark matter halos, it was basically, you really needed a rho going as -2 slope to get any side of astrometric signal. A more profile didn't do it. NFW certainly didn't. So that would make me think that at least astrometric microlensing is pretty hopeless with this new density profile. It was possible with the old density profile, but not with the new one. But we haven't quantified that yet. Yes?
Yeah, so do you have any idea of why you're not getting the Archinger slope like
Yes.
quarters?
So we did some numerical experiments to try to figure that out. Why? What aspect of our simulations is breaking it? And the major thing that seems to do it is we can get a steep power law slope. Not quite -2.25, we actually get like -2.3, but close enough. If we just consider a slightly elliptical, so it's not even just spherical symmetry, but a slightly elliptical overdense region with no fluctuations around it. So an isolated overdense region, we collapse that and we get basically the steep power law profile. So what seems to be the critical piece of this puzzle is the fact that the background around the fluctuation isn't completely smooth. And that seems to be what does it. And there was another study that looked at ultra-compact mini-halos about the same time as ours. Their ultra-compact mini-halos weren't as isolated as ours were, but they were finding the same thing, that it's basically the neighboring fluctuations. And after that finding, I kind of took a more critical eye on some of the work that had been done on ultra-compact mini-halos, and there always was a little bit of an inconsistency that bothered me. When trying to figure out the velocity dispersion of the particles that were forming this thing, they just used the standard power spectrum to get the velocity dispersion, which neglects the fact that if you have an enhanced power spectrum that makes one of these things, the velocity dispersion is also going to be enhanced. So I think there's basically they underestimated the impact of the neighboring fluctuations and how those give non-radial velocities to the infalling particles, and that leads to the breakdown. But yeah, we can make it. So we wanted to prove ourselves that our simulation was capable of doing it. We can make that density power law. We can actually even make something a little steeper than that density power law by just considering initial condition where you have a slightly elliptical overdensity with no fluctuations around it and no initial velocities falling in.
Well, there is actually an analytic solution, People's derived.
Right, and that's what this assumption was based on, was that if you have self-similarity,
Exactly.
then you get this solution. And so it seems to be the breakdown of self-similarity, i.e. the fact that there is a characteristic scale to these perturbations, that there are other perturbations nearby, is what breaks the density profile.
So what was the lowest redshift that you were able to run?
So we stopped our simulation. So our box size was about 5 kiloparsecs per age. So we stopped the simulation at a redshift of 30, which is about when the box itself starts going into the nonlinear regime.
So do you have any sort of impression for how many of these objects you'd expect to survive to permanently?
So, I mean, most of them, we don't see, up to a redshift of 30, we don't see much disruption at all. I mean, I showed you one, so of our 9 ultra-compact mini-halos, one experienced a merger that slightly made its profile more shallow. We don't, this does not look like a cosmological simulation, right? And it's because it's a spiked power spectrum. So you can see the halos are all kind of spaced fairly regularly. We're counting now mergers. I actually have an undergraduate student who's written a nice code that traces our halos through and counts how many mergers each one has experienced. And yes, they do experience some mergers, but they're not. We don't lose that many halos.
But dumb question. So half the dark matter in the universe is in halos today, roughly, something like that, right?
Yeah.
So shouldn't then half these mini halos be? Because I mean, they're basically unbiased, right?
So yeah, I mean, basically, this is saying that the building blocks of structure formation are these mini halos.
Right.
Yeah. And then we're constraining the dark matter annihilation rate signal from that.
So we just don't know what will happen if they fall into, say, a cluster halo, right? Because they're much denser. So in principle, nothing might happen.
And I would say, all the analytic estimates predict nothing's going to happen. I mean, these things form at redshifts. So the ultra-compact mini-halos formed at a redshift of 1,000. The halos, the other halos here that kind of dominate the halos that dominate the signal that we're constraining formed at a redshift about usually 200 to kind of 400. That's the sweet spot. Forming later than that, they're not as dense, so they're not as bright. Forming earlier than that, they're too rare. So that's kind of the sweet spot window that dominates our constraints. So yeah, they form super early, they're super dense. They can fall into a galaxy and not even notice.
So on this question of the density profile, so then in the top line, then you have a spike and you end up with the r to the minus 1.5, and a plateau, you end up with r to the minus 1, and then the hydrostatic density profile would be r to the minus 2, and that would seem to be in the absence of other constraints would be the lowest energy configuration. So what is constraining these profiles to these particular power law exponents? I mean, so you wonder, like, maybe they didn't have time to evolve all the way to hydrostatic.
Well, they don't have any way to cool.
They're all hydrostatic. It's just with an isothermal.
Yeah.
What you mean is isothermal.
Yeah, exactly.
But there is a whole literature on the question of why NFW has this problem. People don't fully understand.
Don't fully know. This finding of this break in the density profiles is consistent with other findings along similar lines. People have noticed that if you consider the mini halos that form right before a cusp in a cutoff in the power spectrum, they're also finding r to the minus 1.5 density profiles. That's a similar situation because that's just speaking to an absence of smaller scale power. And so I think that's the key, is that if you have a lot of smaller scale power, your structure formation is more hierarchical, more mergers. Numerous numerical studies have shown that mergers tend to push you towards NFW. So no matter what density profiles you throw together, they kind of evolve towards NFW if you keep merging them.
So they don't cool, huh?
Yeah, but so I mean, just to answer you, like, I think that's one important point, Marcos, but there is a second factor that we do know, which is that the shape of the initial peak matters, right? If you start with a power law, you're going to get a power law, you have to because it's self-similar. And so you will get some sort of spike. And if you start with a flatter peak, and you mentioned this right when you said if you have more structure around it, essentially, right?
Right.
You end up with a flatter profile.
Yes.
You knew that on each other. Anyway.
Because phase-space states, they cannot be improved.
Basically.
So let me try.
Go to part 2.
Yeah, let me try to go to part 2.
Yeah.
And then I'm happy to answer more questions of Minihalos, but I do want to talk about the other piece. So this is part 2, probing the pre-BBN thermal history with microhalos. So now we're talking about the gap here.
So just before you talk about microhalos are less than an Earth mass.
Yes.
Right? But if the dark matter has some temperature to start with, you wouldn't make such things because it's below the Jeans matter, below the phase mixing.
you're assuming the dark matter decouples during radiation domination. So that changes this.
I see.
So yes, if this is radiation dominated here, then the smallest dark matter halos you can form are roughly about Earth mass in most ring scenarios. That's not true if this is not radiation dominated. So here's my different view of the gap. If the energy scale of inflation is 10 to the 15 GeV, say, and we have to get to 1 MeV to set the stage for BBN nucleosynthesis, that's 18 orders of magnitude. The universe actually cooled more in the gap than it has cooled since. So this is not a small piece of the universe's history. Us cosmologists should be very embarrassed that this entire region of the universe's history is totally unconstrained and quite unknown. So what are the possibilities? We get out of inflation, we're dominated by a scalar field. A scalar field can either fast roll, that gives you a period of conation. That's actually what I'm going to talk about at the luncheon, so I'm not going to talk about that now. I'm going to talk about the scenario that it oscillates at the bottom of its well here. Then it behaves like a pressureless fluid, and it's basically matter. As far as the expansion of the universe is concerned, it's a matter-dominated era. Perturbations in the scalar field indeed grow linearly with time. Since an oscillating scalar field behaves like matter, it's actually going to overtake radiation. And so you will get a matter-dominated universe. This can happen with the inflaton, it can happen with string moduli, or it can happen with other massive particles. This is a really generic feature of several of the hidden sector models of dark matter that have been proposed recently. All we know for sure is eventually whatever was dominant during this early matter-dominated era decays into radiation, thus reheating the universe, and the reheat temperature, which is the temperature at the onset of radiation domination, has to be greater than 3 MeV in order to get everything set up right for BBN. But at temperatures higher than that, we really don't know. So what I'm putting in here is basically an early matter-dominated era, right in here.
So, just to be clear, the usual picture is that the reheating happens as soon as inflation stops.
Yes, a
But
rapid
you're-
decay.
Yeah, but you're saying that this doesn't have to be.
Doesn't have to be, or it's quite possible that even if that does happen,
Yeah.
that other particles that are present would then
Then
come
decay
to
and come. Okay.
would then come to dominate before decay.
Thank you.
But don't you need to do it at hundreds of MeV to get QCD phase transition going?
The QCD phase transition will happen at its given temperature, regardless of what the dominant component of the universe is at the time. So when you cool the primordial plasma to about 170 MeV, you will get the QCD phase transition. And it's not terribly sensitive to what the expansion rate is going at that time. So this has two major implications that I'm going to discuss. Dark matter production and early structure growth. So I'm going to go through the dark matter. Actually, I'm going to skip straight to the dark matter production that I really care about, which is thermal dark matter production. So this is density, this is scale factor. I'm going to call it a scalar. It could be any other massive particle. It's just nice to call it a scalar to distinguish it from what will be our dark matter. It's dominant during the early matter-dominated era. So it's redshifting away as 8⁻³ until it decays. Radiation is being sourced by this decaying scalar field. And so it redshifts away as 8⁻³ before transitioning to kind of the normal 8⁻⁴. Dark matter goes into thermal equilibrium with the radiation bath and freezes out, just like normal. However, the freeze out of the cross sections you need to get the right freeze out abundance are significantly smaller than what you need if it freezes out during radiation domination. And that's because after it freezes out, more radiation is being created, so it's effectively diluting the dark matter abundance. And so you need to freeze out with more of it. So this is why these scenarios historically have been considered kind of nightmare scenarios for dark matter, because they require a dark matter annihilation cross-section that's so small that you would never ever see it. And this plot is a plot I stole from one of my favorite papers of all time, Kinetic Decoupling, 2006, that shows the relic abundance as a function of dark matter mass for different reheat temperatures and different amounts of non-thermal production of dark matter. And the different points here are different SUSY models. So the fact that there are any blue points on the red line, which corresponds to observations, is the so-called wind miracle. But the key is that if you mess around with the reheat temperature and you mess around with non-thermal production, you can get all these models to predict too little dark matter or too much dark matter. The title of this paper was actually The Right Relic Abundance from any SUSY model.
The only problem is SUSY is not found at the LHC, so it may be wrong, the wrong model, so it's a blessing that it doesn't exist.
Well, I guess more saying that, we would like, what this paper really inspired me to start thinking about this subject, because I used to think that, one thing we know about dark matter is if it's a thermal relic, it has this cross-section. And that's not true.
That's
You
what
can actually
everybody
get,
says, but you're
right,
telling us not
but the
so.
relic, if you mess around with the early universe, you can get the right relic abundance from any cross-section. High, low, it doesn't matter. So, how can we get out of this mess? And this is the microhalos. So during the early matter-dominated era, if you have your dark matter fluctuation, it enters the horizon and it experiences linear growth, just like in a matter-dominated era. And it will transition to logarithmic growth when the universe becomes radiation-dominated. This leads to an enhancement of power on small scales. Now this is an enhancement on sub-horizon scales, so that's why these mini-halos are smaller than my previous ones. My previous mini-halos came from enhancements in the primordial power spectrum, so we were much more free about what type of scales we could talk about. These are constrained to be sub-Earth mass because of the reheat temperature. They have to be sub-horizon at the time of BBN. This leads to an increased amount of inhomogeneity on small scales. So this is Earth mass, and when I said sub-Earth mass, I meant it. That we've got the flat line here is what you would get, assuming no cutoff from free streaming, etc., from just a normal radiation-dominated evolution. It's very, very flat. This is why all structures form at the same time in standard cosmology. And here, if you add in an EMDE, you enhance this inhomogeneity on scales less than the horizon mass at reheating. These will give you microhalos. Now, free streaming will suppress this. And so you can calculate the free streaming horizon, and that will lead, instead of a limitless enhancement, that will lead to a leveling out. And in fact, you only get that the structures grown during reheating only survive if the free streaming horizon is 10 times smaller than the reheating horizon. So, what does this mean for microhalos? This is now press sector predictions for what is the content, what is the fraction of dark matter that's bound in halos with masses less than the reheat mass as a function of redshift. So if there's no cutoff, then it's just 100% of the dark matter at arbitrarily high redshift. But of course, that's not realistic. If the cutoff is 40 times the horizon, you get over half of the dark matter already bound up at a redshift of 400. If it's only 10 times, then you've got to maybe wait to a redshift of 100 to get appreciable amount of microhalos. Either way, it's much greater than the standard scenario in which you don't really get any microhalos at all until a redshift of 50. So in these scenarios, with these cut ratios of 40, 20, 10, you really are talking about most of the dark matter being bound into these sub-Earth mass microhalos. So how then do we calculate what this will do to the annihilation signal? So this is a picture of a Earth mass mini-halo that forms in a standard cosmology versus one that forms after an EMDE. These are simulations. And you can see that the one that forms after the EMDE actually contains many, many, many smaller halos that have formed even earlier. So that's why we think that then it's basically microhalos all the way down.
By the way, you have roughly the mass of all the asteroids in the solar system, roughly the size of the Kuiper belt kind of thing. It's interesting. It's like the solar system asteroids.
Except they're puffier. They're much bigger. So the typical scale radius of these things.
1% of a parsec, you say?
Yeah,
That's roughly the Oort cloud. I mean, it's
and then the objects themselves, that the asteroids are much more compact
Sure.
than the halos. So, to just do a first pass estimate of the boost factor, the dark matter annihilation rate is proportional to the density squared integrated over volume, so that's this J factor. If you consider instead a halo filled with microhalos, then you want the profile is basically given by your number of microhalos plus a component from the smooth halo, which is actually negligible. The number of microhalos is given by some kind of survival probability, and then this bound fraction that you can get from crash factor theory. So this is my first analytical pass at calculating what the boost factor would be. And so the major assumption I made was that all microhalos have NFW profiles with C equals 2 at their formation redshift. Remember, these are microhalos that are forming from a scale invariant power spectrum. So these are not the same ones that got the Moore profiles earlier. And we found that they're not really susceptible to stripping, not in a way that really appreciably affects their annihilation. So then we can estimate a boost factor. And given the bound fractions that we got from Plateau theory, we're getting boost factors on the order of 10 to the 5 if all the halos that are formed at a redshift of 400 survive, down to a few hundred if you assume that only the halos formed at a redshift of 50 survive. So these are enormous boost factors. However, as I mentioned earlier, in these scenarios you need to suppress the annihilation cross-section to get the right amount of dark matter. So you have to take the cross-section down, but then you have this enormous boost factor bringing you back up. And our first pass bound, so this shows the boosted, kind of particle physics contribution to the annihilation rate as a function of reheat temperature. The curves here correspond to curves that give you the right relic abundance. And the black lines are the current observational constraints from the isotropic background to the dwarf spheroidals. And for masses less than 100, 150 times the reheat temperature, it's basically just enough. The boost is just enough to compensate for the suppressed cross-section and make these potentially constrainable. So we did that. We looked and looked at isolated Beano dark matter to give it a concrete model. So this is Beano dark matter. Beano dark matter is widely thought to be ruled out because it overproduces the dark matter, except not if there's an EMDE, then it gives you just the right amount. However, it's also very weakly interacting, couples very early, rather cold, and meets all the requirements to make this scenario work. And so this mechanism can make the so-called isolated Beano dark matter detectable. However, there are caveats, two major sources of uncertainty. What about the small scale cutoff? What exactly is it? Where should it be set? How does kinetic decoupling and free streaming differ between an early matter-dominated era and a radiation-dominated era? The answer is a lot. And then the next question is, do these first generation of microhalos survive? I.e., is it really microhalos all the way down? Do the earliest forming ones survive being absorbed into larger microhalos, which then get absorbed into larger microhalos, which then fall into galaxies? Another piece of caveat is these constraints were all done from annihilation. Microhalo-dominated emission does not follow a typical annihilation profile. Annihilation profile should be proportional to density squared. But if the signal is actually coming from a bunch of mini-halos or microhalos that are spread throughout the halo, then the actual signal from the halo should go as density. So it's actually more similar to decaying dark matter than annihilating dark matter, albeit that because the halos tend to be destroyed in the central region, it's like a decaying dark matter signal with the central region suppressed. And we're actually looking into that as well. So I kind of am running very short on time. Let me make a couple mentions, a couple of broad scale strokes about the small scale cutoffs, since there were a lot of questions about that. So the first thing we wanted to look at was, what does kinetic decoupling do during an early matter-dominated era? This is the first potential source of a cutoff. So now we put in interactions between dark matter and the radiation. So this is the evolution of the density perturbation. This is scale factor. The mode enters the horizon here. It's initially coupled to the radiation. Notice the radiation is behaving oddly. The radiation does not oscillate during an EMDE because it is being perpetually sourced by the decay of an increasingly inhomogeneous scalar field. So you actually end up with perturbation growth in radiation and then kind of a steady state. Dark matter then decouples and catches up to basically where it would have been if it had never interacted. If it stays coupled longer, you can get bizarre things where the dark matter then falls into the underdense regions and then falls back into the overdense regions. And if it decouples very late, you still get an enhancement to the dark matter perturbation, it's just inverted in sign. So basically what's happening here is the radiation is flowing out of the overdense regions. It's being perpetually replaced by the decaying scalar field. But as it flows out, it's pulling the dark matter with it. The dark matter actually then accumulates in the underdense regions. If the scalar field decays before it decouples, it just stays in those underdense regions. If it decouples first, it falls back into the overdense regions. Either way, it doesn't give you a cutoff from the power spectrum. Free streaming is even more complicated. So this is the equation that governs the evolution of the dark matter temperature. And usually this equation has two clear asymptotic solutions. If the momentum transfer rate is greater than Hubble, then dark matter temperature tracks radiation temperature. And if it's much less than Hubble, then dark matter temperature scales with 1 over a squared. That's the standard story. Something different happens during an EMDE. During an EMDE, the scalings are such that the dark matter temperature never fully decouples. It actually scales as a to the minus 9/8 during the EMDE. What this is saying is that the extremely rare collisions are still putting in enough energy into the dark matter to keep it from cooling adiabatically during the EMDE. We don't know yet what this means for free streaming. We're working on that. But this is quasi-decoupling, discovered by another one of my graduate students, Isaac Waldstein. All right, so I'm going to wrap up there. I'm going to leave on a picture of we have been running simulations of EMDE microhalos. So this is with an EMDE, this is no EMDE. And you can see indeed, this is with a K-cut ratio of 20. We're getting microhalos at a redshift of about 200. And those microhalos are more or less surviving to the end of the simulation at a redshift of 30. So that seems to be not a source of concern. So I will end there. Thanks for your time.
So two questions related to each other. So for direct detection experiments, they might not see anything, and then suddenly such a microhalo comes, and there will be a huge signal. So I wonder. And the second thing also related is, if you have a clump of dark matter coming to the solar system, wouldn't it be easier to trap it gravitationally
because it has a slower, it has individually a lower velocity dispersion inside relative to itself.
But also it can interact with Jupiter. It's more massive than a single particle coming through. So gravitationally it can be trapped.
So the sticking point here is there is a reason why these are isolated dark matter models. So these models, because they have the smaller annihilation cross sections, generically have extremely small direct detection cross sections as well.
But if a clump passes by,
even with the clump passing by, that boost in the ambient density is not. So remember, kind of the annihilation boost was just enough to kind of bring you back to recover the ground you lost. Because it's not density squared for the direct detection, that isn't quite enough to get you back to radio loss. Plus, I remember very early on I did some rough calculations, and one of these should only pass through our solar system like every 10,000 years or something. So our odds of seeing one are small. So you're
then Neanderthals may have seen it.
And so the possibility that we would see one is small, and even if one did pass through, chances are it's not going to be enough to actually see it, because these, there is a link between annihilation cross-section and direct detection cross-section. And if you suppress one, you generically suppress the other as well. which is good for us. That's one of the reasons why these things don't have as much of a free streaming length as you're used to, and the fact that they decouple earlier. But it's just bad news all over the place for direct detection. I have nothing of comfort to offer the direct detection people. They better hope an EMDE never happened.
Dumb question. If something like this passed through the solar system, wouldn't we see perturbation?
It's an Earth mass spread over 1/100th of a parsec.
Yeah, but still.
No.
Okay.
Would the sun care whether or not the Earth just disappeared?
No, but the planets, right?
But yeah, but
No,
if you
not
took the
enough.
mass of the
It's
Earth
very
and
diffuse.
spread it.
Yeah. No, I hear you. I mean, we are very good at this, right? We can, we have laser ranging to the moon and all that stuff.
I don't know.
Not
I mean,
that
Planet
good.
9 was barely found, Planet
Yeah,
9.
that's true.
It's an Earth, more than 10 Earth masses. Planet 9, just recently.
So,
all of these limits are coming from Fermi upper
yes.
limits, right?
Yes.
So
So far.
the question is dark matter annihilation. The assumption is that it will produce something that Fermi would detect.
Yes.
Is that something that's completely natural, or do you need this additional some level of fine tuning that it will produce gamma rays that Fermi would see?
So actually, generically speaking, you don't expect it to annihilate straight to gamma rays. You expect it to annihilate to quarks or leptons that then decay into gamma rays. So the question that I hear you asking is how plausible is it that it decays to that it annihilates to anything in the visible sector whatsoever? How do we know it doesn't annihilate straight to like dark photons?
Or even photons that are not in the Fermi band.
Oh well, I mean, if the particles,
Those are dark.
so
Those are exactly, yeah, dark photons. Thank you.
so I mean, generally speaking, if it's higher than Fermi band, it will cascade down to Fermi band, at least to some extent. There is a range here of how sensitive Fermi is to cascades, and you have to work through all that. But generically speaking, if it goes higher than Fermi, it will cascade down to Fermi. Not to mention that we also have pretty good bounce from galactic center Hess observations at the higher masses. If it's so light that it can't annihilate in Fermi's band, it's too light for me to care about because it doesn't freeze out before like BBN.
I see. So your mass range is
My
in the
mass
Fermi.
range is exactly where Fermi's window is.
Okay.
The mass range that I care about is Fermi's mass range. Now, then your question of does it annihilate to anything we can possibly see? I would say that.
Neutrinos, for example.
What was that?
Like neutrinos.
It's actually very difficult to get something that would annihilate to neutrinos and not to leptons. I mean, if it's via the weak force, then it should go to both leptons and neutrinos.
But there are some bonds from neutrinos, right? I mean,
Oh, and then there are some bonds, but those are weaker. But I'm saying more generically in particle physics. If you annihilate to neutrinos, you should also annihilate to positrons and electrons and all that stuff. So more it's more like you annihilate to a dark photon. So then you get into, we do have good constraints on dark photons. I mean, bounds on N effective are pretty good now.
Really? From what?
From the CMB.
For simply, the degrees of freedom in the early unit.
Wow.
So
Really?
yeah, from the cosmic microwave background.
I didn't know that. Okay.
Yeah, there's not much dark radiation out there. There's certainly not enough dark radiation to pair produce all the dark matter we see. So if it annihilates to dark radiation, that means it was also pair produced from dark radiation, which means there should be a thermal bath of dark radiation that is the origin of the dark matter. We definitely don't see that. So in these kind of hidden sector models that I mentioned as being one of the motivators for an EMDE, what happens is the dark matter is actually pair produced from some dark gauge boson, like a dark Z, that then couples via a singlet portal to the standard model and then decays. So then you get an early matter-dominated era from these gauge mediators, but they in turn decay with lifetimes well less than a second, because they got to get out of this off stage by BBN, into standard model particles. So in those scenarios, what you have is dark matter annihilation to dark particles, which then rapidly within a second decay to visible particles. We'd still see them.
Any other questions or comments? If not, let's thanks for speaking again.
Something doesn't cool.
was brilliant, very nice.
Yeah.
Therefore,
And
it's no
I
interest.
guess I was not in your state.
It's ignorable.
Which is it?
It's ignorable, of course.
Okay.